My name is Alex Coomans, and this is Dan Nee. We both work at Square. If you haven't heard of us before, we make one of these things. We're most known for credit card processing for small businesses. We offer a bunch of other things, but that's kind of the core thing people know us for. But today we'll be talking about metric storage, collection, and visualization at scale.
So just to start off, what we'll discuss today. So just to begin with, just what are metrics, obviously. Why are they important? Metric basics, common setups, and then we'll go into more about our setup at Square and what we do at scale. So our storage system, our collection system, our visualization system, and then at the end some lessons learned from deploying all of this. So to begin with, what are metrics? These are your QPSs. These are the numbers that represent what's happening in your infrastructure. So these are your QPSs, your response times, physical resources, etc. Cool, that's pretty simple. So why are they important? One issue that metrics help solve is when you're capacity planning. So we actually have an internal tool that uses metrics and past behavior to try and predict earlier when we might have capacity issues across our entire infrastructure. Monitoring your systems is hard. Building checks into your application works sometimes, but your application isn't an alerting system, and it shouldn't be. And also what happens when your app goes down and it can't alert you. It's always best to cover your bases in as many ways as possible. And that's what metrics are for. They make that a little bit easier. So as an example, this is a graph that shows the number of jobs in a specific queue during an incident. It normally hovers around 80 to 100, and as you can see, it went a bit higher that day. And so right around there is when our alerting systems detected that something was abnormal and paged an engineer. And so an important part of metrics is that engineers need to understand why they were paged. And if you see a page like this, you'll want to see graphs that show you, what led to you being paged. Is it a general slowdown and the queue has been slowly increasing for a while, or was it a sudden spike? However, once you've been paged, you actually need to investigate. So being able to correlate events across potentially multiple systems is paramount. Was there a recent deploy? You should roll it back. Is it my entire app, or is it just pieces? Or maybe it's a downstream dependency.
So some of the metric basics we'll be talking about today, and I'll kind of allude to, are some of the basic data types that we kind of store and talk about. So the first one is called a counter. So these are monotonically increasing numbers, normally from when your application starts. So often, like at Square, we use these to track the number of requests since the application has started. So here you can see this is an example of a counter of the number of RPC requests a specific handler has received in one of our staging environments. You can see that it resets a handful of times to 0, and that's when the application was deployed by our automatic deployment system. So then next up, you've got gauges. So they're instantaneous measurements of a value. So for example, the number of current DB connections. So these lines happen to represent the percentage of DB connections used on one of our bigger database clusters. So you can see some of them are hovering around 50, 60, and then other ones are barely even used. And then you've got histograms. So they're calculating statistics on a set of numbers. So often this is things like response times. So you'll calculate percentiles. How many? So if you hear like 95th percentile, that means 95% of your requests roughly are being served in that time or less. So here's a latency graph for the RPC handler I showed you for the requests a little bit ago. The green line at the top is 99th percentile, yellow is 95th, red 75th, and the blue is the median. So essentially that means we're serving 95% of our requests faster than 500 milliseconds, but for some of our requests, about 1%, we're sometimes 3 times slower than that. So that's just a bunch of numbers, right? That sounds really easy. So by the numbers at scale, at Square, we ingest about 250,000 metrics a second for about 13 million unique metrics total, and we have 100% desired uptime. While that sounds nice and fancy, we have a ton of engineers relying on this data to be available for alerting, and missing that kind of data means a missed page, and that's really bad. We deal with money, and people don't like when money doesn't go the way they want. So common setups, and these are ones that we've run at Square, and you've probably seen or maybe even run them yourself. So Graphite or Whisper. So most people think of Graphite, they think of the web UI. But specifically, I'm going to talk about briefly the storage engine that it ships called Whisper. It's an RRD-like fixed space storage system that stores each metric in its own file. So there's pluses and minuses to this. One, it's very easy and simple to get set up. If you want to start monitoring some of your applications, you just kind of throw this on a box and start sending metrics, and then you kind of are done. Fairly simple to set up. But we eventually moved away from Whisper due to our need for a distributed replicated system that partially didn't require manual configuration for each node, and then we were starting to hit some resource limits of at this kind of numbers per second, you eventually just run out of I/O when you have a single box. So then we moved towards a system based on OpenTSDB and HBase. OpenTSDB is a distributed time series database that is built on top of HBase. And so HBase is an open source distributed file system essentially modeled after Google's Bigtable. However, we eventually started hitting some issues that we'll talk about a little more later, but the primary issue was storage. You start running out of it stores every data point, at least it did back then, and so you start to run out when you have 250,000 metrics a second, and you store those for a week or a month or a year or maybe 2 years. You start to need a lot more disk capacity than the people who have the money, the checkbooks want to give you. So here's our current setup at Square. On the left is our collection pipeline, so applications, databases, and other components of our infrastructure emits metrics that travel through our distributed streaming platform into our time series database called Blueflood. On the right is our visualization and query pipeline, where we have front-end applications that query and process metrics data in Blueflood for our users to read. And we'll start to go into these parts in more detail. So first up is storage. So storing every data point forever is very hard. This is kind of the core portion of our scaling problem. It requires a ton of storage, both from a disk space and a cost actual dollars. It can be very slow. Queries for large ranges like a month or a year would be loading tons of data. For example, at Square, we report metrics every 30 seconds mostly. So a month of data is about 100,000 data points for a single series. Your computer screen can maybe render 2% of those points. And that's just a single series. Maybe you're looking at 20 different hosts. Now you're at 2 million data points. Hand in hand with that, it's also really inefficient, right? Most of the time, you either want to see granular real-time data, like what's going on with my application right now, what's going wrong, or look at historical trends. For example, you may be debugging an issue and realize, oh, it's just a capacity-related issue because your QPS has doubled in the past month and you didn't plan for that. The answer to a lot of these issues is called Rollups. So at Square, we store all data points as published for 24 hours after which we start rolling them up into 5-minute buckets. So we roll them up by taking a set of data points and calculating the min, max, and mean and storing those points instead. So here in this blue dot, you can kind of see we've already rolled up data older than 24 hours and 5 minutes ago. And then the next 5 minutes between that and 24 hours, we need to roll up. So we'll take those 10 data points between 24 hours and 5 minutes ago and 24 hours ago and calculate the min, max, and mean on those three and store that at the 24-hour mark. So this process continues on. And as you can see, we just went down from 10 data points to 3. So, however, we don't just stop at the 5-minute bucketing. We actually continue to roll these up, and we get less and less granular as time goes on. So here you can see a bunch of rolled up points that we have every 5 minutes. So at Square, after 30 days, we start actually rolling up those 5-minute buckets into 30-minute buckets. So the same process as before, but now we instead take the min of the mins, the max of the maxes, and the means of the means. So you'll see all those data points disappear and turn into one data point at 30 days. So now we've gone from 10 data points to 3, and then you keep going out, and then you keep getting less and less storage needed. So rollups, as I kind of said, as time goes on, you kind of bucket these points together. But for it to work really well, you need a resolution-aware query system. Let's just go down. Hello? Okay. So otherwise, you can't always get the math to work the way you want and get the accurate numbers you want. So this is Blueflood in our system, the core portion. Blueflood was originally designed as a product called Rackspace Metrics by the company Rackspace to support multiple customers as kind of like a hosted solution. So they would host it for you, and you would just send them their metrics. But they open sourced it so that they have multi-tenant support kind of built in. We don't really use that, but it's kind of nice. And it uses Cassandra as the underlying data store. And as I mentioned, the reason we chose Blueflood as we were moving away from OpenTCP was because it was rollup aware and it was resolution aware, and it was able to handle these kinds of issues that we were hitting. And another reason Blueflood works really well is that it uses Cassandra, and Cassandra is really well suited for time series database. And Blueflood also has built-in protections against failure beyond what Cassandra helps provide, which Dan will talk about in a minute. The query and ingest pieces are simple and have no internal state, right? They're just querying Cassandra, super simple. But the rollup piece, however, is slightly more complicated since you need rollups to continuously occur. So we use Zookeeper, which is a distributed coordination service, in case you haven't heard of it, to coordinate rollups between nodes. So our metrics namespace is sharded into 128 slices, which are split across the nodes that perform rollups. If a node happens to disappear, the rest of the nodes in the cluster automatically take over the unowned shards within about a minute. So Dan's going to kind of talk about how we use Cassandra.
Yep. So as mentioned, Blueflood uses Cassandra as its data store under the hood. And just to give a quick overview, in case you're not familiar with it, Cassandra is a popular and distributed NoSQL database that is easily scalable and highly available. It has tunable fault tolerance, and data is replicated to multiple nodes. And it can tolerate the loss of a node without losing any data. It's written in Java, and Square has lots of experience running Java applications. And later I'll go into why we love Cassandra for our purposes. To give an overview of the Blueflood data model, there are multiple Cassandra tables that Blueflood uses, but the main data is stored in a series of 6 tables, one for each resolution of data that is stored. So in Cassandra tables, there's a partition key and a clustering key. The partition key is what is hashed to determine the distribution of the data across the cluster, while the clustering key is what determines how the data is sorted within a partition. And so in Blueflood's case, metrics data is distributed across the cluster according to the metric name, and data is sorted according to the timestamp. So in practice, data is distributed fairly evenly, and queries across sequential time ranges are very efficient. For example, querying for the last hour of data fits the model pretty well. So here are 2 of the metrics data tables that are stored in Blueflood. The one on the left is for full resolution data, and that's what's actually written to as metrics are ingested. And the one on the right is for 20-minute resolution data. As mentioned before, you can see that the data is keyed by the metric name, and it's sorted by timestamp, allowing for efficient queries. And you'll also notice that the 20-minute resolution table holds 3 different numbers in the value column, one for min, max, and mean. As you may have guessed, these correspond to the values that result after we perform rollups. One of the biggest reasons we love Cassandra for metric storage is that it's a natural fit for time series data. So time series data is typically append-only and immutable. And since you're only ever writing new data points and you're only ever writing them once, Cassandra's data model is great for handling sequential data. And since data is always sorted, it works extremely well with this kind of workload. We also love Cassandra at scale since it's optimized for writes and easily handles our high write, low read workload. For time series, you're always writing new data, but reading that data happens much less often. And as mentioned before, we currently ingest around 250,000 metrics a second, and that doesn't even include the writes that we do when rolling up data. Square is growing extremely quickly, which means we have to deal with an explosion in the number of applications, servers, databases, and all the metrics that these components emit. Fortunately, Cassandra, being a distributed database, is very easily horizontally scalable. If it turns out we need more resources to keep up with our growing metrics load, all we have to do is add more nodes to the cluster, and it'll automatically rebalance itself. Also, part of rollups means that we don't actually want to keep our data around forever. So if we're downsampling full resolution data to 5-minute resolution, we obviously don't want to keep the full resolution data around. For a lot of other databases, we would have to set up a background job or something like that to periodically clean up data. But Cassandra has built-in support for expiring columns, which means that we don't have to worry about deleting data, as Cassandra will take care of that for us.
Sweet. So now that we've got a place to store our metrics, how do we actually get them there, and how do we collect them? So collecting, metrics about your entire system is very difficult. A number of difficulties include, it's a major distributed systems problem. It's even more difficult when you want to make sure that all the metrics published by a client are actually 100% stored. So at Square, we have an SLA of if you publish a metric, we'll store it, and it'll be there. So making sure that this happens all the time is a bit challenging. So we're going to be talking about the left portion of our system. So the core kind of portion of our metrics publishing stack is called Apache Kafka. It's a distributed pub/sub streaming platform. So it transports messages on topics which are logical grouping of messages. So think you'd have a topic like metrics, you'd have a topic like logs, and you can put anything else you want on there. Each topic is made up of one or more partitions, which is basically a simple ordered queue. So you put stuff at the end, and then you have something reading at off the front. Partitions are then distributed across what Kafka calls brokers, which are the leaders responsible for handling all reads and writes and replicating them to one or more backup brokers for redundancy. To scale up the system, you just simply add more partitions, more brokers, or both. So how does that translate into metrics? We use protocol buffer messages, which are similar to Thrift or Avro, if you've heard any of those. But essentially, it's a really compact data serialization format. And then we submit those onto the metrics topic that we have for each individual data center. Then our metric system subscribes to those topics to consume the metrics off the pipeline and then stores them in Cassandra. So here's an example. This is actually the protocol buffer we use at Square to help ship metrics around. So you see we've got a field for the name of the metric. We've got a field name that kind of indicates the type of the metric. So we use count for counters, value for gauges, and then histograms have like median, sum, and then a handful of percentiles. So 75th percentile, 99th percentile, and all that. And then we have a timestamp field for the number of milliseconds since epoch. And I'll talk about why that actually helps us make this much more stable and much more scalable in a minute. And at the bottom, you can kind of see we've got the two values. You can either give us a long value or a double value. We use a long value to represent large numbers that we want exact precision on, so things like counters. And we use double values for things like percentile values. So here's a basic overview of how our Kafka clusters are set up. Square operates two main data centers on each side of the United States, and we have a handful elsewhere in the United States and abroad, but this is just kind of a simplification. But our primary compute power lies in the W2 and E2 data centers. That also happens to be where we have our metrics clusters. Each data center has its own Kafka cluster, and then what we do is we mirror topics from the data centers that don't have metrics clusters into those that do. This also helps our HA story, as we can either fail into or out of a cluster that's having issues. So, for example, if one of the clusters is having issues forwarding out, we can fail out of that, so we have real-time metrics for the rest of the infrastructure. But we've had cases where we actually fail into the problematic data center because there's another that might be related to another incident that's going on right now, and we need real-time metrics for that data center more specifically. Also, our visualization layer even allows you to kind of split brain, so you could query both if you really needed to. So, say, for example, a metrics message is published to the Kafka cluster in our W1 data center. It'll then get replicated to our W2 and E2 data centers, where our metrics clusters can consume it. However, a message originally published just to the Kafka cluster in our E2 data center will only be published and replicated to our W2 data center because it's already in the E2 one. So Kafka promises at least once delivery semantics, meaning that if a consumer happens to die before it's able to acknowledge a write, when the consumer on that partition restarts consuming either the same application on the same box or maybe a different one, they'll reconsume the same metrics again. So this is kind of where that timestamp field comes into. So by the fact that our proto contains that timestamp, and since that's used as part of the clustering key in Cassandra, it actually realizes that that's just a duplicate entry and then accepts the write but drops it. So we can just kind of keep consuming, and we don't really notice very much when we reconsume duplicated metrics. So application metrics. So some languages can efficiently submit directly to Kafka. This often works best in languages where you have real threads and a single running application. At Square, our Go and Java applications can easily submit metrics, and they do that every 30 seconds in what we call a batch metric event. Essentially, it's the proto I showed you earlier, just a bunch of them and compressed even a little more because they're all values sampled at the exact same time. So as I mentioned, we use things like counters. So the problem is, to keep that counter, you need some type of shared program state. We also want to submit to Kafka off the thread serving requests, right? You don't want the thing submitting to your logging system or your metric system to block or delay your actual request serving. So unfortunately, in languages without real threads or sometimes very odd deployment models, that can be challenging to achieve. So we actually have what we have is a solution called Collector. So Collector is for generic infrastructure monitoring or otherwise applications that don't have threads or can't easily submit to Kafka itself. It's really great for simple scripts, something that everyone knows how to write. It simply expects scripts to output the metric name, a space, and the value. And then that's it. It takes care of publishing it to Kafka for you. It runs on every box in our infrastructure, and our deployment system makes this really easy to hook into. So one of the tools that we run, that Collector runs, that we use to monitor our physical infrastructure, is a tool called Inspect. So Inspect is an open source tool that we wrote for instrumenting hardware and MySQL. So it collects things like C group metrics, CPU, memory, disk, file system, network interfaces like kernel, TCP statistics, really lots of the stuff that can really figure out what's going on. Our database team also uses this to collect metrics for MySQL, which you'll see some pictures of a little bit later. So here's a picture of the command line, and you can kind of see it's a little small, but you can kind of see there's a bunch going on. But even at the very bottom, like, it identifies problems, what maybe on this box is causing issues. So this is the GUI, but there's an API that is what we use to hook into. So our deployment system, which is called P2, which is also open source if you're curious, uses a YAML manifest similar to something like Kubernetes to dictate exactly what should be deployed and the configuration it should provide to the application. It also allows hooks to execute during phases of a deploy. So we have a hook that executes and reads this configuration and writes out the configuration that Collector needs. So for this exact config, Collector will run the bin stats inspect script out of the deployed application. Every 30 seconds, collect those metrics and ship them off to Samza, or our Kafka clusters for us. So here's another example, very similar. We've got a script that we distributed as part of our core set of monitoring tools that parses IPMI output and generates metrics on things like CPU temperature and fan speed. Those are the things that you don't think you need until you really do. So next up, Dan's going to be talking about visualization.
Okay, great. So we've got all of our metrics in one place in Blueflood. Now, how can we make use of it? So the crux of the visualization problem is that making time series data human readable is hard. Having all of your data in one place isn't very useful if there isn't an easy way to get that data out and onto your engineer's screens. As mentioned before, Square collects around 250,000 metrics every second for a total of around 13 million metrics. The large volume of unstructured metric names makes it difficult to search for and analyze metrics that are relevant to a particular host or app, service, data center, or whatever you're looking at in particular. So here I'm going to be talking about the right side of this diagram, which is our visualization system. So for engineers to easily query and visualize their application metrics, we built an open source application called Metrics Query Engine, or MQE. MQE has a SQL-like interface to query raw time series data in Blueflood, and it provides powerful functions to aggregate, filter, and analyze. MQE uses tag-based metrics to structure metric names so they can be easily queried and discovered. So if you're not familiar with them, what are tag-based metrics? Well, in the traditional Graphite representation of a metric, all information is encoded in a single string delimited by periods. So here we have a metric that is collected by Inspect, and it measures the CPU usage of Blueflood within its C group. Tag-based metrics, on the other hand, represent a time series using an immutable string name and a set of key value pairs as metadata. So the same Inspect metric can be represented using tags by separating out the data center, host name, and service name into tags. And also, different time series with the same underlying measurement can be represented under the same name, just with different tags. So for example, if we measure the same metric on a different host, all that changes is the host tag. The structure of the tag form highlights all the ways in that the metrics are the same. Tag-based metrics are nice because they're self-describing, meaning any user should be able to look at the metric and understand what it means. They also allow for easier and more powerful aggregations and grouping. For example, you can easily aggregate this metric across all of the hosts in the West 1 data center, for example. So now let's walk through an example of what you can do with MQE and tag-based metrics, so you can see what that looks like. So here's a query for the previous metric, CPU usage, and it's in the form of a query language that MQE can understand. So what we're doing is we're querying for this inspect metric name, and we're filtering only by metrics that belong to Blueflood services, and we're limiting the results to the past 2 hours. And since we're using tags, it's easy to filter the results across dimensions like service name. And this is nice because it's in a structured query language that most engineers should be able to understand. So here's the graph you get when you actually input that query into MQE. Since we don't specify a data center or host, MQE expands this particular time series out. So we get a separate line for each host in each data center, and that's why there's so many lines here. Obviously, there's a lot of data, and it's not that useful. So instead, what we can do is we can tweak this query and invoke an MQE function to aggregate and sum across all these different lines. So now we have the total CPU usage across all of our Blueflood services, which is great. But it turns out that we actually lose a lot of information by aggregating everything together. So instead, what we actually want is to group this information by each different Blueflood service so we can differentiate them. So in MQE, we can do this by using the group by keywords as part of the aggregation function. So now we have the total CPU usage for each Blueflood service in its own line. This gives us a pretty good idea of how each Blueflood service is performing, and it's a relatively simple query. CPU usage is great, but what's even better is knowing how much of our total CPU we're using for our Blueflood services, and that's what the second metric measures. In MQE, we can select 2 different metric names in the same query and aggregate across a common set of tags. So here we can see how our usage compares to our total number of CPUs available. And what's even better than that is knowing exactly what percentage of CPU our Blueflood services are using, which we can do by simply applying an arithmetic operation between 2 different names, and we're still aggregating across and filtering by a common set of tags. And if we only want to see CPU usage in a single data center, all we have to do is specify another tag filter in the where clause. And so here I've added an and DC equals west1 to limit the results. So there's an endless number of ways you can filter, transform, and aggregate your data. You can even forecast future data by estimating best fit lines or using other models like Holt-Winters forecasting. You can easily extend MQE with your own custom functions, and you can also directly examine the tags for a metric. So you can do cool things like list all the clients that are talking to your service, or list all the hosts that have Java apps running on them. Of course, we don't want our engineers to have to type in complicated queries if their applications are misbehaving during an emergency. So we've created a metrics dashboard, which provides an easy UI for analyzing metrics for your application, MySQL clusters, servers, whatever. With metrics dashboard, engineers can easily utilize MQE to slice and dice their metrics, filtering across sets of tags. And what's more, metrics dashboard automatically detects if your application is emitting a certain type of metric, and it pre-populates your dashboard with useful graphs. So for example, if you're spinning up a new Java app, metrics dashboard will automatically detect that and create a dashboard with all metrics about your JVM. So your memory usage, your garbage collection stats, etc. During incidents, engineers can quickly view their metrics dashboard and diagnose problems in real time. So here's a screenshot showing an example of a metrics dashboard page that's powered by MQE. This particular page surfaces metrics for the MySQL database that's actually powering the metrics dashboard UI. In fact, this page is auto-generated by metrics dashboard by detecting which metrics are relevant for the particular component you're looking at. So our goal is to make it easy to view your most important metrics from day one without any additional configuration on your part. You should be able to build a new service and then go directly to metrics dashboard and see your metrics right away. Looking at this page, you can see that it's easy to switch to viewing only data centers you're interested in just by clicking a button. And as you can imagine, this maps directly to an MQE filter. It's also easy to switch from a real-time view of your most recent metrics to analyzing historical trends using this time selector on the left, which is also maps directly to an MQE query. Metrics dashboard has a bunch of features that make it super useful for engineers. One cool feature is graph annotations. You can annotate your graphs with important events, and so you can see at a glance why your graphs might be all wonky. In this screenshot, the blue dots are annotations that I've made, marking some important changes. And the best part about the annotation system is that it's hooked into our deployment system. So anytime you deploy your application, it's automatically annotated on your dashboard, which makes it super easy to correlate abnormal behavior with the most likely causes. Cool.
Awesome. So there's some lessons we've learned as we've grown our system from a very small metric stack with just a handful of applications at Square to thousands of servers, hundreds of applications, and a service-oriented architecture. So the first one is determining whether or not you want to use rates or counters. So rates are better when you use rollups. The math works better. But if you're using counters, that works better if you don't use rollups. We still use counters mostly because of legacy reasons. We started off with a Graphite system where counters work better. Now that we're on a rollup based system, it actually would be better, and we're looking into switching to rates because the math works better. If you're curious, I can show you a bunch of graphs. But essentially, to get the math to be more exact, it's a lot easier to use rates.
An important operational lesson we've learned is that it's really, really nice to have multiple metrics clusters running. So in our case, we have two independent but identical storage and collection clusters running. Each cluster collects and stores the same metrics, but only one is ever active at a time. So obviously, this is great for disaster recovery. If one of our data centers goes down, we still have the other metrics cluster up and running. All we have to do is fail over. And speaking of failovers, they're super easy with this setup. At any given point in time, our visualization systems are pointing at just one of the two clusters. And if we need to fail over, whether it's because of a disaster or simply just for planned maintenance, all we have to do is change the front ends to point at the other cluster. And the transition is seamless and invisible. And finally, one major reason we moved on to Blueflood is that our previous system didn't scale well with the number of metrics we were handling. So if we had one bad actor in the system, such as a single application sending thousands of dynamically created metrics, it could have toppled our entire metric stack. Blueflood scales much better to this type of explosion, but ideally you still want some kind of mechanism to stop this kind of thing from happening in the first place. We've learned that limiting the number of metrics that a single entity can send to our stack can be extremely helpful operationally. Not only are we protected from bad actors DOSing our system, but we're also able to more accurately plan capacity for Blueflood since we know that there's a limit to the amount of growth we can experience. That's all we got. Any questions?
Yes. So the rollups, do they occur in Blueflood?
Yes, Blueflood. So there's a Blueflood server. You can like toggle different modes. So we have nodes that handle query and ingest independent. So independent of the ones that do rollups, and then they just kind of chug along and they figure out what needs to be rolled up based on. Blueflood has some internal tables that it uses to track what's dirty. So like if it happens to receive in things after it's already rolled up, we have our time limits that. Your metric has to be there within a certain amount of time, and then we don't start rollups until after that. And then we realize, okay, so we wait 4 hours until we start rolling up the first bucket, and then if any metric's older than 4 hours, we just drop it on the floor because most of the time that means the system's NTP clock is off.
And how does it perform? Do you see any major performance dip when rollups are undergoing?
Not really. I mean, they're always going on, so it's not really like a big kind of like spike and then drop. We used to have some issues where, and this is actually why we now wait for rollups to occur until 4 hours, which is what our cutoff is for ingestion. So what happened is if there was a bad system that came up with maybe an hour off clock, it would start sending metrics, and then we'd re-roll up points. It also happened if our Kafka pipelines, sometimes they get backed up. If there's a forwarding issue or something, so let's say one of the data centers has an issue forwarding to the other one, then if those metrics are delayed, then they could be delayed a little while, and then they would re-trigger rollups for that shard because the shard is just kind of a hash on the name. So that's why we kind of just said your metrics have to be here within 4 hours. If not, they're dropped, and then after that, then we start rolling up so that we don't really have to worry about those types of things. But it's kind of a steady performance or steady kind of amount of work it has to do. Yes. Not really. We don't really. Often, it's not used as extensively. Our Java and Go applications are the primary ones that submit metrics because they're the primary portions of our infrastructure. Most of the system ones are mostly run by our team. So like the inspect stuff is run by our team. So we kind of control a lot of that. Not that any application couldn't do anything bad there, but in general, the rate limiting happens at a higher level instead of at least at collector's level. And then it's kind of easy to tell if it's which host it is because it has the host name in the metric.
Also, so in the Blueflood, it looks like the string or the metric name in the row key list is the flight contamination graphite style of the tags and all that. So how do you handle mapping tags to metric names when you're searching?
Yeah, so we have a separate service currently that maps Graphite like string names into tag-based metrics, and that's sort of separate from the main like Blueflood pipeline, but that sort of goes on and it's like additional metadata inside Blueflood, and then MQE reads from that to get the tags. Yeah, so it's additional process right now. We're currently working on making everything into tags, so we don't have to do that additional step.
What's the total size of your infrastructure for using the 13 million metrics?
We've got, I think, 20-something nodes in each of our data centers, so 40-ish total that handle all of that. So, I mean, I think our metrics clusters represent less than 1% of our overall infrastructure. Yes. Alerting on metrics. So we use Nagios for that, so that it calls into Blueflood, and then that's how it does it. We don't currently do stream processing. We've kind of experimented with it, and part of the problem is to try and get. So Kafka doesn't necessarily guarantee. It guarantees ordering within a partition, but since we publish metrics in a batched event, they may not always go to the same partition, so you can't necessarily guarantee that you'll receive the timestamp at 30 seconds ago and 60 seconds ago in that same order, so that it makes it a little more difficult to do that kind of thing. If you used like static hashing, where you always put host 1 and west 1 on partition 4, then you might be able to do something like that, but we currently don't. We just call into our metric stack anyways. Yes, sir. We build that completely from scratch. So the main reason we built that was because our application engineers, we had a previous dashboarding system similar to Grafana, but slightly different. It just mostly called into Graphite. But the problem is engineers wouldn't maintain their dashboards. So the biggest issue is that during an incident, we'd be like, hey guys, where are your dashboards at? And they're like, well, we didn't think to do those. So the biggest thing about Metrics Dashboard is that it's automated. So about 99% of the dashboards people look at on a daily basis are auto-generated. So if you add a new RPC service, any handlers, anything that changes, we automatically detect that and then update your dashboard. So it just kind of loads and you're like, oh, cool, there are my RPC handler graphs. Like, great. So unfortunately, like sometimes we have like issues. You're like, oh, if I have 100 action RPC handler, there are some makes it a little crazier. But the biggest reason we built it this way was because we needed people weren't maintaining their dashboards, and during incidents, it was essentially wandering around in the dark. Awesome. Well, thank you very much. And if you guys have any more questions, you can chat with us too.